In this lesson, we're going to explore the derivative of an exponential function. We're going to follow the derivation of those rules. We're going to know which function is its own derivative. And finally, we're going to use those new derivative rules to find derivatives. All right, so let's go ahead and start by just looking at our basic function, f of x equals a to the x. So this is an exponential function where our a is greater than 1. So it's a growing function. And as we look at this, we can see our slope is just slightly bigger than 0 here. And our slope keeps getting bigger and bigger and bigger. And so if we were to draw its derivative, we would start kind of near 0, but above, and then have it getting steeper and steeper and steeper. And we'll see that it has the same shape. All right, so let's go ahead and take the definition of a derivative to go ahead and figure out what's happening here. So when we take the definition of derivative, first we're going to have a to the x plus h minus a to the x all over h. We're going to then do a few algebraic things with this. First, when we add exponents, that means that it could start out as a multiplication problem. So a to the x times a to the h minus a to the x all over h. And next, I can see both terms have an a to the x, so I can factor that out. So the limit as h approaches 0 of a to the x, a to the h minus 1 all over h. And then in my next step, I'm going to write this as two separate derivatives. The limit as h approaches 0 of a to the x times the limit as h approaches 0 of the rest of it, a to the h minus 1 all over h. And these are the same because if I multiplied a to the x times this, I would get what's right up here. Now this first limit's really easy. There is no h here, so no matter what h does, this is just a to the x. And that's why when we drew the derivative, we had the same shape, because here's a to the x, and this is the same shape based on a to the x. But over here, this limit equals some number. We don't know what that number is yet. So here's where we ended up. We know that the derivative is a to the x times the limit of this. So we need to figure out what this is. And we're going to do that using our calculator. So here's the limit I want to explore. And we'll take a look at my calculator. You're going to see I already have it in there. A to the x minus 1 all over x. And first I'm going to look at what's if a is 2. So I'm going to just change this to a 2. And I'm going to go to my table. Since this is a limit, I want to clear all of that. The second table, change this over to ask. There we go. There, go to our table. Since this is heading to 0, I want to pick numbers that get closer to 0. Like I might do 0.1 or 0.01. And I want to get it to where the values aren't really changing much. So 0.001, 0.0001. And I can see, let's say I'm going to go one more time, 0.00001. There we go. And I can see now to the fourth decimal place, it's really not changing. So this looks like it would be about 0.6931. All right. So now I'm going to go to my y equals, and I'm going to change that 2 to a 3. Then I can go to my table and see what happens here. And I've got the same sort of things. Looks like it's settling in here at 1.0986. 1.0986. We'll do the same thing for 4. So we'll change this to a 4. And again, my table will already be pretty well set. And looks like we're settling in at 1.3863. And then we'll do it one more time with 5. Go to our table, and looks like we're settling in at 1.6095. All right, now those particular numbers probably don't look familiar to you, but we're going to also do this. We're going to find the natural log of each of these. And so actually, just to see it all at once, I'm going to go ahead and just type in ln(a), so ln of our number here. And let's go to our table, but we'll start our table at 2, and we'll go up by 1s, Go back to auto and take a look at this. Oops, I don't want to do that. There it is. And if we look at this, you'll see that, oh look, 0.693, 1.0986, 1.3863, there it is, and 1.6095. Those are the same numbers that we see up there. So I've probably got you convinced. Right now, I don't want you to go away from this thinking we proved it. It's actually the proof of this is kind of beyond our mathematical skills right now. But I want you to see that I've shown you that this limit corresponds to the values of natural log a. And so that gets us our rule. The derivative of a to the x is a to the x times the natural log of a. So the next question is there a special case where rather than multiplying by natural log a, this is actually just 1? So what we want to recall in this case is that the natural log of e equals 1, which means if a is e, in other words, the derivative of e to the x, we're going to get e to the x times natural log e. And since the natural log of e is 1, that actually tells us that the derivative of e to the x actually equals e to the x. All right, so we've got two big rules for today. This one right here, the derivative of a to the x equals a to the x times ln a. And this one right here, that e is its own derivative. The derivative of e to the x is e to the x. With those two rules, we're now going to actually find some derivatives. So our first one, y equals 5 to the x, that follows the rule of y equals a to the x. So when I'm taking the derivative of a to the x, let me just write the rule right under here, I know that I get a to the x times ln a. So my answer over here is going to be 5 to the x times ln 5. And we're done. In our next one, we're combining two rules. Here we also have to remember the rule that said the derivative of a constant times a function equals the constant times the derivative of the function. So 3 right here is our constant, so I'll just write down 3. 2 to the x follows this rule up here, and so we get 2 to the x times ln of 2. All right, our next one here, e to the x. We just learned that the derivative of e to the x is e to the x. So we used our first rule, which was that the derivative of e to the x equals e to the x. The second one is a number. And if I go over here to my calculator and just type in e squared, so second, let's see, e squared, it's a number. Well, the derivative of a constant, you'll recall, this is the other rule we're using here, the derivative of a constant equals 0. So I could write my answer as e to the x plus 0, but of course that's just e to the x. Our last one here, we're going to go back and use this rule of c times f of x. 5 is my c. The derivative of e to the x is simply e to the x. All right, let's try some more. On this page, I would encourage you to try these first before I go over them. All right, welcome back. What we want to in this first problem is recognize the difference between the exponential rule and the power rule. So the derivative of 4 to the x is 4 to the x times ln 4, and then this power rule is the one we learned before, 4x cubed. For this one, derivative of 6e to the x is just 6e to the x. Derivative of root x is 1/2 x to the negative 1/2. And of course, 6 is just a constant, and its derivative is 0. Now, in this last one down here, we want to probably do a rewrite first. So we can distribute this division by 3, and we can even rewrite it like this, 1/3 e to the x plus 1/3. And once we rewrite it, then the derivative is pretty simple. The derivative of 1/3 e to the x is just 1/3 e to the x. And the derivative of this, which is a constant, is simply 0. All right, here's our last two problems. Here we've got e to the pi plus pi to the e. I want you to recognize that this is just a big old constant. It's a number that we could figure out on our calculator if we wanted to, but know that it's just a constant, so its derivative is simply 0. Now this one over here has pi to the x, that's like a to the x, and x to the pi, that's like x to the n, those rules. So for pi to the x, my derivative is pi to the x times natural log pi. And for x to the pi, my derivative is pi x to the pi minus 1. All right, you should be ready for your homework on this section now.